Hello physicists, welcome to our March 24th edition of physics. We are going to start some new stuff today. We are going to be talking about spinning. So chapters 9 and 10 are going to apply the ideas that we've already done to a little bit of a different type of a system. And the system I want you to keep in mind always is something like a bike wheel. Okay, now the thing is, if you just thought about this in too simple of a way, this bike wheel is not moving around a track or anything. And you might say, oh, okay, well, what is its speed? 0. What is its momentum? Well, anything that is going down over here is going up over there. So you add together those momenta, it appears to be approximately 0. However, on the other hand, in a real physical system, I'm taking this thing and swinging it around and having a real tough time controlling it. So it just seems like there's a lot going on in that system, and it's going to be useful to us to invent a language to deal with it. So we've already talked about in the chapters preceding these, how we went from F equals ma to talk about acceleration of objects, to work equals force times distance, to talk about the kinetic energy and the kinetic energy being changed by applying work. And then we talked about momentum, mass times velocity, which is changed by an impulse. So what we're going to do in the next two chapters is that we're going to kind of form a rotational version around this. So in place of F equals ma, we're going to have torque equals moment of inertia times angular acceleration. Okay, so it's going to be similar. There's going to be an F equals ma type of thing for getting objects to spin. In place of mass, we're going to develop an idea of rotational inertia. In place of our work energy theorem, where you put in some work and you change the kinetic energy, we're going to have a rotational kinetic energy, which is the same as your regular kinetic energy. It's just that you're adding up the 1/2 mv squared of every point on the wheel. And as it turns out, this does introduce some complications. So we've so far been very content to have the story that the way that things go down ramps is that they just slide down a frictionless ramp. More common than that is with lots of friction, having a totally sticking wheel roll down a ramp. And it turns out that's quite a bit more involved to describe that, but also more realistic. And so when we go through that, we're going to have to introduce ideas like angular momentum and angular conservation of angular momentum, and it's going to give us new types of problems we can solve, like as I said, a wheel rolling down a ramp, or a yo-yo spinning on its axis, or a gyroscope that's precessing around like this. So we're going to talk about all that type of stuff. It's not hard, but there is quite a bit of new notation. So today's all about notation. How are we going to talk about things that are spinning? And basically, it's all going to involve going from, instead of meters per second, to radians per second, that type of thing. Okay, so what are we going to do when when we're moving in circles? Well, just like in our linear case, we had to choose an x equals 0. And that was a choice. But my displacement along that was more or less fixed after I put that x equals 0, and I define my direction that I mean by plus x. And then you can talk about your displacements, you can talk about everything else. In this case, we're going to be spinning around, and what we're going to do, we are going to define a rotation axis, which we don't really get to choose. Okay, that has to do with the physical situation. So this is my rotation axis. My wheel is spinning around it. Okay? The thing that we do get to choose is our reference 0. So in this case, if I choose a point on the wheel to be my 0, I can go around the circle once and I come back to the same point and I've gone through a displacement of 2 pi, but my choice of the 0 for my coordinate system is just a choice. Okay, so I have spinning around a circle, I've chosen a rotation axis, and I've chosen a reference line. And that's the 0 that I measure all my angular positions with reference to. Okay, now, as people who have taken calculus and all that, you know that we are going to be measuring our angular displacements in radians. And it's a little bit tricky to think about, because a more natural type of human way to think about going around a circle is you say, I went 1 revolution. But 1 revolution is around 6.28 radians. So it's a little tricky to think about. You go around once, and then you've gone 6 radians. But that's in fact just 1 revolution. And, you know, I guess it's also sort of unnatural to think about 360 degrees. But these are different ways of thinking about it. But the benefit of thinking in this way is as follows. If I have an object in the middle of the circle, these spokes are going around a smaller circle every revolution than the things on the outside. Okay, so the things on the outside are going around a bigger circle. So if I'm talking about the V is, let's talk about the inside of a circle and the outside of a circle, this would be your R1 or R2. If you have the speed of a point on this circle and a point on that circle, and they're on the same ray, okay? In linear terms, my speed of the dot on this first circle would be 2 pi r1 over t. So that would give me a v1. And then for my second circle, it would be 2 pi r2 over t. And as you can see, that v2 would be greater than v1. However, if we are just thinking about these in terms of radians, this is the same angle that has been covered over the same amount of time. So the angular velocity of these two is going to be the same. The angular, even though these two, one has covered more distance than the other one, they've covered the same angle. And so it allows me to be able to compare 2 points on the same object with the same number. The same angle is telling me the displacement of this first object, this first point on the object, and the second point on the object, even though the one on the outside is actually traveling farther than the one on the inside. Okay, so that's an important point. Now, there's a little bit of a goofy physics convention, but you do need a convention about this, which is that if you're going around counterclockwise, that is the plus direction for angular displacement. So you would measure an angle like that. That would be something like plus 5 radians, not quite all the way around the circle. But if you go around the other way, that would be a minus direction. Okay, and one way to remember this in your book they say, remember, clocks are good. Or no, wait, they say clocks are bad. That way is hard for me to remember. So counterclockwise is positive. Clockwise is negative. Another way to think about this is you have a hand, and physicists, for probably bigoted reasons of the past, preferred right-handed people. And so if you take your right hand and you go like this with it, that is turning counterclockwise. And your thumb is pointing up, thumbs up. Counterclockwise, thumbs up, that's positive. On the other hand, you look down on your disc and it's going clockwise, that gives you a thumbs down. Thumbs down is negative. Okay, so that's one way to think about it as well. Okay, so just to give you another, sort of a concrete example of this, it says an angular displacement in the counterclockwise direction is positive and one in the clockwise direction is negative. The way that you find your angular displacement is taking your final angular position minus your initial angular position. So let's look at A and B in this case. Now it's a little tricky to think about because every 2 pi you go around the circle again. So, if you have 2 pi, 4 pi, 6 pi, those are all the same position, but you use a different number because it says to me, I've gone around the circle once, I've gone around the circle twice, I've gone around the circle thrice. So that sort of thing is to me the most confusing issue here. Okay, so it says a disk can rotate. Here's just an example. It says a disk can rotate on its central axis like a merry-go-round. Which of the following pairs of values for the initial and final position respectively give a negative angular displacement? Okay, so let's look at A and B. Okay, so in A, it says you start out at -3 radians. Well, what does that mean? It means you start at 0, 0 is the x-axis, and you go over clockwise to -3. Okay, so -3 is just shy of pi. So there's -3 radians. This is pi. This is pi over 2. This is 3 pi over 2. And you end up at 5 radians. So 5 radians is almost 2 pi. So 5 radians is over here. Okay, now let's try to say, what is the story here? I'm going from -3, I'm going to a +5. So how do I do that? I go from -3 to 0 to right around +3 to 5. Okay, so I've gone this way the whole way. Because that's counterclockwise, that's thought of as a positive displacement. If I want to do that with math, it would just be displacement is the final minus the initial. So that would be 5 minus a -3 equals 8 radians. Notice 8 radians is bigger than 6. So what that means is I've gone around the circle more than once. So here's me going, this is 6.28, that's 2 pi radians, and then I keep going around until I get to this point. Okay, so that's what it means to go from -3 radians to +5 radians. Let's do another example here. What if we go from -3 radians, so that's the same place right there, to minus 7 radians. Okay, now this sounds a little bit tricky to think about because here I'm going around. If I go around 2 pi, that's around minus 2.6. Minus 2 pi would be minus 6.28. And so minus 7 is right around here. But because I'm getting more negative, it means I'm going to keep going around clockwise. Okay, so in this case, I would be going around like this. Okay? So, if you do it with math, it would just be the change in theta, the change in the angle, equals minus 7 minus a minus 3, which is minus 4 radians. Okay, so minus 4 is a little bit bigger than pi. Pi would be around half the circle, so we've gone a little bit over half the circle around, but we've gone around clockwise, so we have a minus sign on that. Okay, so I just want to, I've been maybe a little pedantic, speaking slowly, but I just want to say it because I know that this is easy to get mixed up on. All right, now here's a case where, let's say we just don't care about the direction for a second. It says, over the course of a day, this is just an example, 24 hours, what is the angular displacement of the second hand of a wristwatch in radians? Okay, so each minute, I get 1 revolution of that second hand. 1 revolution per minute. So that's the number. Now, it's asking me, over the course of a day, what is the radians per day? So if I want to go from revolutions to let's go from minutes to days first. 1 revolution per minute. I'm going to have 60 minutes per hour. I'm going to have 24 hours per 1 day. And then I need to go 1 revolution is 2 pi radians. Okay, so to get my final answer, I would need to take 1 times 60 times 24 times 2 times 3.14. And there you go. Of course, if you were using your physics convention for this, you would say it would be in minus 9050 radians because you're going around clockwise. Okay, now, the next step that we're going to take is effectively thinking about all of the different variables that we had in linear displacement, or in linear terms, and put them into angular terms. So I want you to write down this with me. Here's our linear, and here's our angular. Okay, so our linear coordinate, when we had a position, we would put it in terms of x, and that had units of meters. For angular stuff, we're going to have theta, which is in terms of radians. All right, now, if we wanted to find out the average linear velocity, we would just take our displacement divided by our time. That was meters per second. Okay, now we would like to have the same type of idea, but in terms of moving around a circle. And so the equivalent idea is going to be this thing. It looks like a W, but every physicist will say omega. So there's omega, and that's in radians per second. Now, if we wanted to talk about how much is my velocity changing per unit time, well, in linear terms, we had the acceleration, which was meters per second per second. In angular terms, we're going to have an angular acceleration. And be careful because this looks a lot like A, but in fact it's an alpha. Looks a little bit like a fish. And that is radians per second. Per second. Okay? But the idea is the same. I have linear position, angular position. Linear velocity, angular velocity. Linear acceleration, angular acceleration. And just like I was able before, let's do linear and angular. If I wanted to find my speed, I would just take the derivative of my position of an object with respect to time. If I want to find my angular speed, so that's going to be my omega in terms of radians per second, that's going to be my change in my angular position with respect to time. Okay, so the way that you get from your position to your velocity is you take the time derivative. The way you get from your angular position to your angular velocity is you take the time derivative. Same thing with angular acceleration and linear acceleration. To go get your linear acceleration, we would take dv dt, or the second derivative of the position. And for our angular acceleration, it would be d omega dt. Okay, so all we're doing here is we're just using our language that we already developed for linear stuff and applying it to angular stuff. Okay, so here's a question. I don't think it's super hard. It's just applying the definitions. This one is part of your new homework. Your homework for today should be handed in already. Your homework, this next homework is fairly short. It is due this coming Monday. Okay, so I tried to make it mostly over stuff that I'm going to cover today in this video. So take a shot at it right after you watch this. But it says, okay, we've got a position here, an angular position that's given by 2 radians plus 4 radians per second squared times time squared plus 2 radians per second cubed times t cubed. Then it asks me questions about what's the angular position and angular velocity at time equals 0, what's the angular velocity at time equals 4, calculated angular acceleration at time equals 2. Okay, well, how am I going to do this? Well, putting time variables in here and getting an angle, that is fairly easy. If you want to find out the angular velocity, that is d theta dt. So the derivative of 2 is just 0 because it doesn't depend on t. This is plus 8t. This is plus 6t squared. Okay, so that's your angular speed in radians per second. And if I want to find my angular acceleration, it would be d omega dt. Okay, so I'm going to take the derivative of this with respect to time. So that would be 8 plus 12t. Okay, so all you have to do in this problem is just do the derivatives, stick in the times that they ask for. It asks, is the angular acceleration constant? Well, no, it depends on t. So this would be a case where you could not use the types of constant acceleration model that we've developed and that we're going to use again for all of our angular stuff. So that's where we're going right now. All right, so just the same way that we did our constant acceleration model. So remember, our constant acceleration model, basically the two equations were this. So this is in linear terms. it was v equals at plus v naught. It said whatever speed you're at the beginning of the story, the acceleration is going to change your speed, so you have to include the t, acceleration times time, and add that on, and that'll give you your final velocity. On the other hand, if you want to find your final position, you've got to take the integral here, and you would have x equals 1/2 at squared plus v naught t plus x naught. Okay, so those were our two basic equations for our linear constant accelerating model. Now what we're going to do is we're going to use that model, but instead of position and velocity and acceleration, we're going to use angular position, angular velocity, and angular acceleration. So what is this equation going to become? It would be something like omega equals alpha t plus omega naught. Okay, so how fast you're spinning at the beginning can change if you have an accelerated angular motion to some different speed. The analog for the displacement would be 1/2 alpha t squared plus omega naught t plus theta naught. Okay, so all they're doing in each of these equations is just replacing x with theta, replacing v with omega, and replacing a with alpha. Everything else is just, it's the same math, it's the same model. So let's take a look at a problem that you could do with this. It says a disk initially rotating at 120 radians per second. Okay, so that's a speed that it's going at. So that would be omega naught equals 120 radians per second. Is slowed down with a constant angular acceleration of magnitude 4.0 radians per second squared. Okay, it's an acceleration, an angular acceleration, equals 4.0 radians per second squared. But they're being a little tricky with us here. They say of magnitude, and they say it's slowed down. So I'm going to put a minus in there. A, how much time does the disk take to stop? Okay, well, I know omega equals alpha t plus omega naught. So they're asking, how long does it take to get to omega equals 0 radians per second? So 0 equals minus 4 t plus 120. Okay, so you solve that, your t would be 30 seconds. All right. And then part B asks, through what angle does the disk rotate during that time? Okay, well, you could go ahead and say your theta equals 1/2 angular acceleration t squared plus omega t plus your initial position. If you just want to take that as 0, it's okay. Sorry, this should be omega naught. So you know omega naught, you know alpha, you know t, you find that. Okay, so I'll let you do that. Okay, so we've talked about how to move from our linear models to our angular models. Now, the next thing I'd like to just address is how do you go back? Okay, and it turns out it's pretty easy to go back because once you have your angular position, you can ask, how far did I actually move? So if you have 6 radians, how far did you actually move around in terms of actual distance? You just have to take that times the radius. If you want to find out if you have your angular velocity and you want to find the linear velocity, you have to take it times the radius. If you have your angular acceleration and you want to find your regular acceleration, you have to take it times the radius. Now that last one has a little hook in it, but the point here is, as I said for our earlier example, if you have a disk, this guy and that guy can be spinning at the same angular speed, but the smaller radius is going to have a smaller linear speed, a smaller linear acceleration, smaller linear change in distance that it's covered than the one with the larger radius. Okay, now what direction does our linear velocity point? Okay, now our velocity, as we said, is just the angular velocity times the radius. Now the direction of it is always going to be just in the direction of the spin. So it's going to be tangent to the circle that it's going around and just pointing in the direction that it's moving. So there's nothing too tricky there. No big change from what we've already done with our centripetal motion previously. There's a little piece of notational change. The time, the period, t, is how long it takes for this point to come back all the way around. So it was 2 pi r, that's the circumference, divided by v, the speed at which this point is going around. So if you wanted to put that in angular terms, so t equals 2 pi r over v, 2 pi r over, and v could be also written as omega times r. So in that case, the r's would cancel out, and you just get 2 pi over omega. So this is two different ways of writing the period. Both of them are fine. This is in terms of radians per second, but radians is kind of a funny unit. You can sometimes pretend like you just got rid of it as in a puff of smoke. It's unlike meters in that way. Now I said that the acceleration was going to have a little bit of an extra tricky part. And here's why that's a little bit tricky. Now, the tangential acceleration, that is the acceleration where, let's say that you're moving in this direction, right? And you're speeding up in that direction. Okay, so you would have v in that direction, and you would have also, you could have an acceleration in that direction if you're getting faster. So the tangential acceleration is speeding up or slowing down. Okay, and so that would be just omega times r. Now, keep in mind there's another type of acceleration that's our centripetal acceleration, and that was always directed towards the center of the circle. So we're going to call that our radial acceleration. If you wanted the total acceleration, you'd have to add these two together as a vector. You'd have to use your Pythagorean theorem to find a magnitude. And that one still, we've called that our centripetal acceleration before. Here we call it our angular, our radial acceleration. The size of that was v squared over r. Now v is still omega times r, so I could just write this as omega times r squared over r. This is omega squared times r squared. R squared divided by r is just r, so this would be omega squared times r, which is what I've written right there. So the thing to notice is that these vectors, the tangential part and the radial part, are perpendicular to each other. So you can consider each individually. Okay, so to round out this video, I'm going to do two examples trying to go and sort of translate between these two ways of talking, going around circles and moving in a line. So here's an example. It says a vinyl record is played by rotating the record so that approximately circular groove in the vinyl slides under the stylus. Bumps in the groove run into the stylus, causing it to oscillate. The equipment converts these oscillations to electrical signals and then to sound. So I don't know if you thought about this before, but if you have you have to keep in mind, if you had the same spacing of grooves at the middle and the outside of a record, your music would appear to get, the pitch would get lower and lower. Or so yeah, well, actually, yeah, I think other way around. Anyway, they have to account for all of this when they press records. Sort of interesting. Okay, so let's see how it works. Suppose that a record turns at a rate of 33 1/3 revolutions per minute. Okay, so that's the angular speed is 33.3 revs per minute. And then 1 rev is 2 pi radians. The groove being played is at a radius of 10 centimeters. So R is 0.10 meters. And the bumps in the groove are uniformly separated by 1.75 millimeters. So delta X equals 0.00175 meters. At what rate hits per second do the bumps hit the stylus? Okay, well, what we want to do is say, well, the speed that we're actually going around, the stylus is actually being, the record rather is being dragged under the stylus is going to be omega times R. But in this case, we want to think about just a little distance on that, a delta X. And how long does it take? How many hits per second do the bumps hit the stylus? Well, the idea here is that V is also delta X over delta T. So if you wanted to find your delta T, it would be delta X over V, so omega R. And then it asks, at what rate hits per second do the bumps hit? So what they want is basically the frequency, which is going to be 1 over delta T. So that's going to give you the amount of times you would get that ridge hitting you per unit time, 1 over seconds. Okay, so the idea is not that hard, but it's very tricky to go between these various ways of talking. Let's just look at one more idea before I let you go. In this one, we have the original Ferris wheel. The Ferris wheel, by the way, was built in the World's Fair in Chicago as the American counterpart to the Eiffel Tower, because the World's Fair had been in Paris the year before, or I don't know if it was just 1 year between them. Anyway, sort of an interesting footnote. The original Ferris wheel has a radius of 38 meters and completed a full revolution every 2 minutes. So the omega would be 2 pi over 2 minutes. So if we want to put that in radians per second, it would be 1 minute, 60 seconds. It says, if the wheel were uniformly slowed down from its maximum speed to stop in 35 seconds, okay, so if we have final speed would be, just to put this another way, this would be our omega naught. If we have our omega equals alpha t plus omega naught, and we're told that the acceleration is going to be in 35 seconds plus omega naught, that's going to be whatever I find here, equals 0. So that would let us solve for the angular acceleration of this thing. It should be negative because it's slowing down. It says, what would be the magnitude of the instantaneous tangential speed at the outer rim of the wheel 15 seconds after it begins its deceleration? Okay, so you know your omega naught, you can find your angular acceleration there, and you could go ahead and find your that omega at time t equals 15 by putting in the omega that you solved for and putting in 15 seconds plus omega naught. And then if you wanted to find the v at that time, it would just be this omega times r, and that would be it. There you'd get your 1.12 meters per second out of it. So there's no part of this that's hard exactly, but it is tricky to keep all of these definitions in play at once. And so that's why I've tried to get you to do a homework that's already going to be due on Monday, just because I want you to practice right away with these definitions. So if you have time today or tomorrow, I'd really encourage you to try it as soon as you can. So big ideas of today: for extended objects that spin, angular coordinates are convenient. Kinematics of linear constant acceleration are going to apply for our angular constant acceleration. And finally, the linear acceleration for points on a spinning object may have radial and tangential parts, because if you're going around the circle, the radial part is about changing direction, and the tangential part is about changing speed. Okay, so quite a bit in this video. Thank you for watching, and good luck with your next homework.